Okay, today is lecture number. So it is lecture number 5. nMOS inverter. nMOS inverter. Okay, let us discuss this topic. So before going to this actual discussion, let us talk about recapitulation of what we have seen in the last class. Recap. What we have seen that we have considered an nMOS one transistor. Okay, and for this we have derived the things. That means we have defined the region of operation of this transistor based on VCS and VTH. If it is less than, or if it is greater than or equal. Okay. So these situations that we have compared based on VCS and VTH. Another one is we have derived that what about VDS, what about VCS minus of VTH. So we thought that what if it is less than and what if it is greater than or equal. Okay, so depending upon these two parameters, we identify that the region of operation of a transistor. It is important when we are realizing the circuits to identify which region of operation the transistor will be, and if you want to change its operation depending upon your requirement. Okay, so therefore we should know what region of operation the transistor is operated. Okay, now let us realize the circuit, a simple circuit, by using these transistors. First of all, we have seen the fabrication of a transistor. We have seen, and what is the construction of the transistor we have seen, and what is its electrical properties. Okay, so electrical properties that we have seen. So we have a clear-cut idea related to the MOS transistor previously. Now, with the help of this particular known device, we want to construct a simple application called an inverter. Okay, so what an inverter will do? Okay, so what is an inverter? A simple digital circuit, okay, which can complement the input at the output side. Okay, it can complement the input value at the output side. Okay, so that means it is a digital circuit. As we know that it is a digital circuit. Whatever the input that you apply here, for example A, it will be complemented at the output side. As simple as that. The question is that how do we realize inside of the circuit? What is there inside of the circuit? So we normally use transistors. Okay. Now, so for any application, whether it is a inverter, whether it is a decoder, whether it is encoder, whatever may be the digital circuits, we have a generalized architecture to implement any circuit. Okay. What we write? There is a generalized architecture. There is a generalized architecture for implementation of circuits, or I can say that for realization of the circuits. For realization of circuits. Okay. So what is this generalized architecture? So this generalized architecture consisting of a network, two networks that we have to consider, something like this. Okay. So these networks are connected and take a common point as an output. Okay, we have to apply the inputs for these networks. And very essentially, we have to connect this one network to the power supply VDD. Another network is connected at the ground. Okay, so this particular network, network which is connected to VDD is called pull-up network. PUN means pull-up network. So PUN stands for pull-up network. Pull-up network. So another network is there that is called pull-down network. So PDN stands for pull down, DOWN down network. So these are how we normally call it as. So what is there inside of this pull-up network? What is inside of this pull-down network? And what kind of devices that we have to use for these networks? Okay. First and foremost important thing is that what is the responsibility of this pull-up network? Responsibility of PUN. So what is the responsibility of this PUN means? So this network always connect the output signal towards the VDD side. The network is responsible to pulse the output towards the high supply or VDD. Okay. So I can simply write here is one statement. It pulls up. It pulls up the output towards high value, towards high sub, high voltages or high sub, high voltage or VDD side. I can simply write it this way. Similarly, I can say that what is the responsibility of this? What is the responsibility of this pull-down network? Okay. So let us write here. So pull-down network. It pulls down. It pulls down the output towards low voltage. So that's very important. That means it's towards the ground side. So this output will move towards this side by the PUN network, and this output will move towards the VDD side by using the pull-up network. Okay, that is what the responsibilities of these networks. Okay. Now the next question is, what kind of elements or what kind of devices that I have to use for pull-up and pull-down, right? Now, usually, I think another color, right? Usually, either resistor I can use this, resistor, nMOS I can use it. It can be depletion. It can be depletion, or it can be enhancement. Okay, either one is possible. Similarly, I have to go for PMOS also. It is possible to use the PMOS transistor as well. Okay. But in case of pull-down network, usually we consider nMOS transistors only. nMOS transistors only. So this is what the networks having the different kind of elements. Are you agree with me? Okay, this may be a resistor. It may be a resistor. It is an nMOS. It may be, or it may be PMOS. But here we normally consider nMOS only because of its huge advantage is there, okay, when compared to the other elements. Fine. Now let us realize an NMOS inverter with the help of a resistive pull-up network. Our objective is realization of an inverter using resistive network, using resistive circuit, resistive circuit at the pull-up network. Okay, so we are going to realize an NMOS transistor with the help of resistive circuit. How do we do this one? So let us simply write in this way. So I'm going to consider a resistor at this pull-up network. Okay, but as usual, we know that we have to consider an NMOS transistor. We have to consider an NMOS transistor. So this common point we normally call it as voltage output. Normally we have to take the output as a voltage, not a current here in this sense. Okay, and this is connected to VDD. This is connected to ground. This is input is connected to VAR. Voltage input that we have to apply. So this is called an NMOS inverter with resistive pull-up. What we can call it as is an NMOS inverter. It is an nMOS inverter with resistive pull-up. Resistive load anochu, resistive pull-up anochu, whatever it may be, it doesn't matter. Okay, resistive pull-up or resistive load also. Normally people will normally call it as a load. Okay, so therefore here we normally consider this is called a pull-up network. So pull-up network, and this is called pull-down network. Okay, whatever may be the circuit, we can use this is the approach, but depending upon the application, number of transistors will be increases, and we find some kind of difficulty of using this resistor also. So let us now look at what kind of difficulties we face if we are using the resistor pull-up, all these things. Okay. Now, as I mentioned that it is acting as an inverter. How this circuit will act as an inverter? That means that whatever the input that I'm applying here, that means V out should be not of VAM. So this is what it has to do. Whatever the input that we apply, it has to go as a complement at the output side. So whether the circuit is operating the same way or not, we should look at it. Okay. So that is called an operation of inverter. So let us write operation of or working principle on operation of inverter. Okay, so better I have to consider this diagram. Place copy, and I can paste it here. I don't need this kind of pull-up representation and pull-down representation. Okay, now see here. So before going to this understanding of the operation of this device, let us understand some basic points related to this device. Okay. Okay. Observations. We write some observation. What are the observations? Number one observation is that we are going to construct a digital circuit. We're going to apply a digital circuit, which means that we are going to apply either the binary bit 0 or binary bit 1. Okay, binary values that we have to apply. So what I can say that, so binary values. Binary values. What do you mean by a binary value in the sense that logic 0, binary 0 stands for, it can be a ground or it can be called as logic 0 or it can be called as logic low. Either name is possible for this one, or it may be some zero value. So 0 volts also we normally consider 0 volts also 0 volts. Similarly, the logic 1 or a bit 1 can be considered by VDD high supply, or I can call it as a logic 1, or I can call it as a logic high value, or it is a 5 volts also. Okay, it's depending upon what kind of technology we are using, but usually we consider it as 5 volts. Is it clear to all of you? So we are considering only the binary values. Okay, but that means we want to implement the digital circuits, not the analog related circuits. Okay. Now, the second point to remember here is that the second point is what happened if you are applying the binary values to MOS devices? Operation of or state of the transistor. Okay, I can simply write that the state of the transistors. Okay, a simple notation is that, for example, if you consider here is, for example, if you consider here is an nMOS transistor. Okay. If you apply logic 0 here at the gate, logic 0 or binary 0 if you apply, it will be considered as an open circuit. It's a open, or it is called as off transistor, right? Similarly, if you consider an nMOS transistor having logic 1, if you apply logic 1 we apply, then it will be considered as a short circuit. A short circuit is observed and it will be considered as on. So that's what the first attempt that we have to understand. For nMOS transistor, what happened for the nMOS transistor if you apply logic 0? What happened if your logic 1 is applied for a nMOS transistor? Okay. Opposite behavior is observed for a PMOS transistor also. It is an nMOS, as everybody knows that. It is an nMOS, right? If you consider the PMOS transistor, opposite behavior can be observed. What is the opposite behavior? For example, a PMOS transistor represented in this way with a bubble. Okay, if you apply logic 0, now it will be acting as a short circuit. So I can simply say that it is a on transistor. It's a on. So that means whatever the signal that is applied here, that will be transferred towards the output side. For example, it is an input and output. This is input, this is output, for example. Okay, similarly, we considered another transistor here. What if you apply the logic 1 here? So it is simply off transistor. That means the signal cannot go to the output side because it is off transistor. Okay, since the opposite behavior that we can observe also. Is it clear to all of you? So this fundamental 2 points that we have to remember while you are understanding the operation of the transistor. Once it is on, what kind of notation it is there, it's a different issue. But thing is that when the transistor is on, when the transistor is off, by applying the digital inputs for a MOS transistor. Right? Fine. Now, let us apply that same kind of theory at this point. Okay. Let us apply same kind of theory at this point. Now let us see the case number 1. Okay, case number 1. Now we have a possibility of applying the input at the VAN. Okay, then we want to take the output at this point. So let us consider, let us apply VAN is equal to logic 0. Let us apply VAN is equal to logic 0. Then what will happen here? What will happen? What is happening here? Observe. As I mentioned that if any one of the gate, if the input of the nMOS transistor is at logic 0, this transistor becomes off, right? This transistor becomes off. Okay, so that means this transistor becomes off. Agreed? Now, carefully, you have to understand one point here. So this is actually two networks that we are having, right? Here, let us consider in this pair. That means that here, some amount of the current will flow and some amount of the current will also flow here also. Okay, since it is a two networks that are connected, the series connection is there. So this network having the current some X, some current Y observed here. Similarly, there is some amount of the current will flow here. There is also some amount of the current flow here also. Okay. Similarly, here also we can observe here the current is flowing here. This current is called, let us consider IR, resistive current. And here also some current is also flowing. So that current is called IDS, right? Drain to source current. This is normally called as, right? So what is happening here if Vn is equal to 0? Immediately we have to understand that IDS value is equal to 0. That's what we identified from the electrical characteristics. If the MOS transistor is off, means it is in the cutoff region. Cutoff region, IDS value is equal to 0. Clear? Then what happened to the IR then? Since it is a series connection, so pull-up network and pull-down networks are in series connection. If IDS one network having the ID current value is 0, upper one is also 0, right? So therefore, which makes that IR is also equal to 0. Agreed? Series network. So if IR is equal to 0, what is the drop between this? What is the value of the, so now what we want to calculate finally? We want to calculate what is the Vout at this condition. So in order to find out the Vout value, therefore we have to calculate from the VDS value to 0. From VDS value is equal to 0, sorry, IDS value is equal to 0 means VDS IR is also 0. If IR is equal to 0, what is the drop here? What observe that IR is equal to drop means IR is equal to 0 means the voltage drop across the resistor is also 0. Why? Because why it is so? Since VR is equal to IR into R. Because IR is equal to 0, what is the VR? VR becomes 0, right? Voltage drop is equal to 0. So if voltage drop is equal to 0, what do you mean by this one? Voltage drop between the voltage drop across the resistor is equal to 0 means it is a short circuit. There is a short circuit between VDD and Vout. VDD and Vout, right? There is a short circuit between VDD and Vout. So this short circuit resemblance, what do you mean by the short circuit resemblance? Short circuit resemblance is the potential difference is equal to 0. That means the short circuit means, what does it mean? Here is a VDD, here is Vout, which means that Vout is equal to VDD. Vout is equal to VDD kada. Since it is a short circuit means both are at the same potential. That's what the meaning. Vout is equal to VDD. So that is what we observe. That is what we observe. See here what happened. If I'm applying the VN is equal to 0, what I'm getting here, the result will be, result is, what is the result? V out is equal to VDD. VDD stands for logic 1, right? So VDD stands for logic 1. That means V out is equal to logic 1. When you apply a VN is equal to logic 0, what we are getting at the output? Result will logic 1.
Hello, sir.
Is it clear to all of you what we have done so far?
Hello, sir.
Please remember that when VN is equal
Hello.
to 0, VN is equal to 0, the nMOS transistor is in the cutoff region, which leads to IDS is equal to 0, which in turn makes the IR is equal to 0. Thereby, the voltage drop across the resistors is equal to 0, which means that it is a short circuit. Which short circuit means source the VDD and Vout are at the same potential. Therefore, Vout becomes VDD. VDD is nothing but logic 1. Or 5 volts it is. Clear? Fine. Now, what happened if you apply logic? Let us apply. So this theory is very important because it's the same kind of analysis that we have to do it for the depletion mode, enhancement mode, and CMOS inverter also. Okay, so please remember. Next case number 2. Case number 2. What is the case number 2? So obviously the case number 3 is equal, Vn is equal to what happened if you apply the logic 1. Okay, logic 1, let us apply. So the similar argument that we do here also, but in a different manner. Okay, so look at here, copy, paste it here. Okay, so what is happening here? Observe, say ground, VDD. So when I'm applying the Vn is equal to 1, it's simply on transistor. The transistor becomes on. The transistor becomes on. So on transistor, we talk about that one later on. So it is simply, a short circuit. It's simply a short circuit between VDD and ground. Now what will happen here? So here the current flowing here is IR. Here the current flowing here is IDS. Is that IDS 0 here in this case? No, it's not equal to 0. As we know that when the transistor is in on, finite amount of the current will flow. Okay, but the two possibilities are there. Either resistive current will flow, or the linear current will flow, or saturation current will flow. Agreed? So now the question is that how much amount of the Vout we observe? That's an important one. How much Vout that we have to observe? So two things that we have to observe. Number one is First point is, once it is on, we have to observe that what is the state of what is the state of this transistor? Okay, first point. The second point is that what is the value of Vout? What is the value of Vout? What is the value of Vout? Okay, so assume that the state of the transistor we look at later on for the after some time. First, let us understand what is the value of the Vout. Okay, as you can see here, this output is connected directly to the ground. Okay, because of its short circuit nature. We expected that Vout value is equal to ground. We expected that Vout value is equal to ground. Expected. But it is not ground value. But Vout is not ground value. It is the true. So why it is so? Vout is not going to zero, but actually it is near to the zero actually. So the truth is that it's not equal to zero in the sense it is near to the zero. Okay, it's very important to remember. Nearer to the ground or logic zero. So in that sense, Vout value is equal to result we are writing here, result that we are writing as Vout value is equal to ground approximately. I can say that approximately. We trace this point after some time. Okay, so therefore, whenever I'm applying the logic high value here, okay, whenever I'm applying the logic high value here, Vout becomes logic zero. Vout becomes logic zero. Ground means logic zero, right? So therefore, the inversion behavior is observed when we are talking of when we realize the circuit in this fashion. Okay. Therefore, our conclusion. What is our conclusion? When VAN is equal to logic zero, Vout becomes logic 1. When VN is equal to logic 1, Vout is equal to logic 0. Okay. Now, as I mentioned that we don't have any problem with this here in this case. Case number 1, no problem. No problem. So good logic high value that we got. Good logic high values. But when we achieve this logic low value, this is called, there is a problem. There is a problem in finding the Vout. Let us see what is its Vout exactly. How do we calculate this one? Okay. So because in the Vout in the first case, the transistor is in the cutoff, we don't have any problem. But in the second case, Vout is the transistor is actually on transistor, but we have to justify that whether it is in linear, whether it is in saturation. So based on the current equation, we should say that the transistor is in which mode of operation, right? So let us investigate that part. Finding VOH. Finding Vout low value. Output low value, or people will call it as output low value. Output low value. Or normal in the literature you can find VOL, output low value. Okay, how do we do this one? For that one, as we know that First of all, we have to derive the voltage transfer characteristics of a MOS device. From there, we can calculate. Okay. So first one, voltage transfer characteristics. What do you mean by this one? Which means that whenever we are applying some input voltage, how we are getting the output voltage. That's what it says that. So whenever we are applying some input voltages, then how we are getting the output voltage. As we know that when the input voltage is 0 volts that we apply, 0 volts, or I can say that logic 0 if you apply, we know that this value becomes VDD. That's what we calculated. When the VN value is equal to VDD, for example, highest voltage that we apply, okay, so this is what we can normally write it. This value becomes 0. Vout is equal to 0. Agreed? So when VN is equal to 0, that means 0. So we can observe VDD value that we got. When VN is equal to VDD, Vout is equal to 0 that we got. Then what is the transaction between VDD to ground? So VDD to this value. So whether it is going in this way, or whether it's going in this way, whether going in this way, which way that it has to go. Anyway, from large value to the low value, it has to move. The output should go from high value to the low value. Therefore, that is the high value here to the low value, the output has to move, right? That's what the inverter will do. Inverter input అనేది low ఉన్నప్పుడు high అవుతుంది, high ఉన్నప్పుడు low. That means output will move from high value to the low value. So how it is moving? That's the question. Okay. For that one, what we should know that this is identified from the region of operation of the transistor. This is identified from the region of operation of the transistor. Please remember carefully. We know that we have a resistor here. We have a resistor here. We have a transistor here. When the input is equal to 0, we applied. What is the Vout value? We found it's a VDD. Okay, so that means this transistor is initially off transistor. So that's the reason why we got here is Vout is equal to VDD. So Vout is equal to VDD, right? Are you agreed? Agreed? Now that means that this transistor, when it becomes it is off, that means that here it's happening. Okay, when this transistor becomes on, as we know that VCS value is greater than threshold voltage of this transistor. That means that if the input voltage is greater than or equal to the threshold voltage, this transistor becomes on. That means that we have to wait up to the threshold voltage of the input voltage must reach to the threshold voltage. Okay, for example, here is the threshold voltage. When Vn is equal to threshold voltage, up to that point, the transistor will be in the off mode only. So up to that point, the Vout is equal to VDD only. Clear? So therefore, I can simply write the Vout is equal to VDD up to VTH. Agreed? The output value is equal to remains there at VDD as long as Vn is equal to less than VTH. Okay. Now I am increasing this value from 0 to VDD, that I'm increasing this value, input value. Okay. So slowly I'm go to the threshold voltage of a transistor and move forward. Okay. So that means that you can say, and it reaches to VTH of the transistor, for example. Yeah, it is reaches to the threshold voltage of the transistor. Then what is the value here we observed? Here is VDD only. Up to VDD here is VTH that we have applied. Observe carefully. So the input is at some low value, output is at high value. So threshold voltage is 0.4 only, VDD is 5 volts. 0.4 on conductor, 0.4 on a threshold voltage. 5 volts is here is a 5 volts. So what is the mode of operation of this transistor? As we have seen the region of operations, Anyone from the class? I told you some shortcuts. Anybody guess? The gate is at low potential and the drain is at high potential. You can also type it in the chat box also. Anyone from the class? The gate is at low potential and the drain is at high potential. So what is the region of this transistor, whether it is in linear or it is in saturation? Anyone? Please respond. What is the region of operation? What is the operating mode, whether it is in saturation, whether it is in linear? So please remember that, as we have mentioned previously, when the source is at a ground potential, if the gate voltage is greater than the threshold VD, then it is in linear. When VC value is less than VD, then it is in saturation. So if the input voltage is at threshold voltage at the gate and the drain is at 5 volts, 0.4 is less than 5 volts. So that means that here is the 0.4 only we have applied. Here is 5 volts is already available because of previously. So here up to this point, this is the 5 volt voltage only, right? So therefore, it is in saturation. So it is in saturation. So, but it is in the saturation, but where it has to go? It has to decrease fashion. It should be in the decrease fashion, something like this. It is in the decrease fashion, right? So here the MOSFET is in off mode, cutoff. Here the saturation, it is in the saturation. It is in the saturation. So another thing is that our scenario is something like this. The input is rising and output is decreasing. This is what the scenario that we observe, right? So in this particular scenario, we are keep on increasing the VTH value. So keep on increasing the input voltage. We are observing that keep on decreasing the output voltage. So initially the transistor in the cutoff, then it moves to the saturation and keep on increasing the VTH, keep on increasing the input voltage. The output value is degraded, will be decreased. That means that it will enter into this region, right? Then VC values at the input side is increases and Vout value at the output side is decreasing, right? That means that the transistor will enter into linear region. Okay, it's not that it remains in the saturation region. It will enter into the linear region also. So at what voltage the transistor will enter into the linear region? That is the question. Point is clear? The question is that at what voltage, at what input voltage, at what input voltage transistor enters into linear region? That's the question. Okay, so when it will enter into that region, any guess? Another equation. What is the equation? We know that we have to take the relationship VDS and VGS minus a VTH. This relationship is more than sufficient to say that whether it is linear or saturation region, right? So it must be equal. So we can consider the edge of the saturation. We can consider. What does it mean? As we know that, for example, so this is the point. This is the point is called edge of saturation. That means edge of saturation. So this point onwards, if this point is moving this side, means it is in the saturation. If this point moves this side, linear region. That means that is the junction point. So therefore, the junction point will decide whether it is in the linear or whether it is in the saturation. Okay, normally it is in the less than equality that we have to consider. Okay, So or maybe less than also we need to consider, it doesn't matter, but this is the point where exactly the transistor will decide which region of operation it will enter. Look, in this sense, what is the VDS value? As we can see from the output, the diagram. So in this diagram, VDS stands for VD of the transistor is at the output, right? V out minus of the source is at 0. What is the gate at the VAN? Source is at 0 minus of VTH. So therefore, V out is equal to VAN minus of VTH. So the V out is equal to VAN minus of VTH onwards, the transistor will enter into the linear region. Can you guess where exactly the VN minus of VTH is available? Yes, here. So from this point onwards, this point onwards, VN minus of VTH. That means total is actually VN. దాంట్లో నుంచి threshold voltage తీసేయటం ఇదే కదా తీసేయటం. So this is the region that we want to remove. So that the remaining portion, this one only. So from this region onwards, we can see that one. Okay, what is the relationship between V and V out? V out is linearly proportional to that of VN. Linear with VTH. Sorry, VAN. అంతే కదా. So VN ki V out relationship ఏంటి ఇక్కడ? Just mathematical equation, straight line equation. So linear equation. So therefore, I can simply write a straight line from this point onwards. Okay. So what is this equation we can call it as? V out is equal to VAN minus of VTH line. Okay. As we keep on increasing the VAN value, what is the V out value? V out also will change us accordingly. Okay, so that means at this point onwards, the transistor will enter into linear region. Okay, so therefore this value will go and go into this way and linear region. So, but it cannot go to 0. So let us investigate why it is not going to 0. Okay, so therefore the transistor will enter into linear region. Okay, we are expecting that this is how it should be. So this we are expecting that this is how it should be. Okay, so it has to go to ground, go to 0. But output is not going to 0. Output is not equal to 0 is observed. Okay, so this voltage we can call it as VOL. This voltage we can call it as output low value. The output low value for a better inverter should be 0. If it is not 0, it is not possible to use for our applications, because inverter is when you apply logic high value, 0 has to be at the output side. Okay, now let us investigate. Okay, what is the time now? So I'll take another 5 minutes, complete it. Okay, so finding the VOL from this equation. Finding VOL is finding VOL. So in order to find the VOL, what is the VN should be? VN should be VDD. VN should be VDD. So we have a small derivation is there. We do this one very quickly. Okay. As I mentioned that, what is the current flowing here? Here is IR. What is the current flowing here? It is ID. For example, IDS means ID. Let us write. Okay, ID. Now what I can write it here? So both the transistors on. So pull up network and pull down network both are on. Therefore, IR equal to ID. Are you agree with me? Since it is in a series fashion, because the MOS transistor is also on. Okay. What is the current flowing through this one? It is nothing but V. Sorry. Here is nothing but V out. This is V out. This is called VAN. What is the potential? What is the current flowing through the resistor? the drop across the resistor divided by the resistor value. For example, resistor R on now. Okay. Now this value is equal to VDD minus of V out divided by R, which is equal to, what is the current equation that we have derived previously? The current equation is actually, it is in linear region. At the near the drain, sorry, near the VDD, the transistor will be in the linear region. That's how we have calculated. Okay, so therefore linear current equation that I have to consider. Linear current equation I have to consider. What is the linear current equation? Linear current equation is beta into VCS minus of VTH into VDS minus of VDS square divided by 2. So what is this VDS value? Sorry, I need to write the brackets at this point, right? So now we have to derive what is the VCS and VDS values at this point also. So beta is multiplied with, what is the VCS? VCS stands for VN minus of VS. VS is 0. It is nothing but input voltage only, that is 0. Therefore, it is nothing but VAN minus of VTH. What is the VDS of the transistor? So this potential drop. So the drain side, what is the potential drop? V out minus of VDD, right? VDS is equal to VD minus of VS. VD at a potential they from the V out, they from the VS is nothing but 0. So therefore V out. So this is nothing but V out. This is V out square divided by 2. Okay. So this is how we need to write VDD minus of V out divided by R. So whatever the V out we calculated here, it is nothing but VOL only. Okay, simply it is VOL. Okay, I can replace V out by VOL. Okay, so therefore it is called VDD minus of VOL. So please remember that this is VOL. Better write this divided by R is equal to beta is multiplied with Bn minus of VTH is multiplied with VOL minus of VOL square divided by 2. Okay, find out what is the VOL here. So it's considered it's a homework. What is the value of VOL at this point from this equation? Okay. So a hint I'm going to give you. So please, I'll give the hint for this VOL. Okay, just wait. Listen. Number 2. Just a second. Just I want to do one thing. So this is the equation that we have to derive. Just I want to copy this one. It's not copied. Copy and then paste it here. So this is for your sake of clarification that I'm giving here. Okay, this is what the equation that you have to derive. Okay, so please. So this is what the equation that you will have. You will get it here. So just to forget, don't worry about it. This one is nothing but a beta. It's nothing but beta only. Here also beta will get. So RL is nothing but R only I have considered. Please try to solve this problem. Okay, and come to the next class. Okay. So therefore, we find that VOL, the output low value should be not less than because of some reason. So it is less than VDD value. Of course, it's near to the zero only you will find because so many negative terms are there in this one. So that's what we can calculate. Okay. So this kind of theory is necessary. This kind of theory is necessary to find out the characteristics of an inverter. So finding the Vout value at low voltage, for that we need to have a transfer characteristics and finding the VOL. Okay. So this is all about the inverter. You please understand this concept by observing the contents that are available here. Okay, we stop it here today. We'll see you in the next class.